Hello everyone, welcome to WB Institution, the online education app. Now we are discussing about design of mission elements. So in design of mission elements we have covered a lot of syllabus, and now we are going to see about design of shafts. So what is a shaft? So shaft is nothing but a rotational member, or we can say it as a mission element which is used to transmit power or transmit motion from one place to other place by use of a shaft. So it is used to transmit power. So basic function of shaft is to transmit power. So shafts are basically in a circular cross section. There are non-circular cross section also, but we are not going to deal about non-circular shafts. Now based on the design of shafts, what we are going to see in the design of shafts. So when designing the shaft, we have to mainly find out the diameter of the shaft. So that is done in design of shafts by two bases, on the basis of two classifications. One is based on the strength, and other one is based on the rigidity. So based on the strength, shafts are generally made up of the material that is ductile material, which will get yield and gets fracture. So based on the strength it will be classified, and based on the rigidity it will be classified. So based on the strength, it is weaker in the shear stress, so we have to calculate tau maximum, and based on the rigidity it will be considered as a theta max. Now based on the strength, let us design shaft. So let us consider a shaft which is subjected to twisting moment and also bending moment. So this is the shaft. Here it is subjected to twisting moment T and bending moment M. So let us take a small element and let us calculate what are the stresses generated in the element, and finally we will find out the value of D. So we have to find the safe diameter of the shaft. Now for shaft, let us take here an element which has two types of forces. One is acting axially and other one is shear stress. So the axial stress is called as sigma B, so that is due to the bending, and the shear stress is due to the twisting moment, that is tau. So how we are going to solve the diameter of the shaft, find out the diameter of the shaft on the basis of the strength, that is on the basis of theories of failures. So which theory of failure is used in calculating the design of shafts? That is maximum shear stress theory. So this maximum shear stress theory is very simpler and also very safer. So we have seen for shear stress other theory also, that is maximum distortion energy theory. So we are not going into that theory. We are using maximum shear stress theory because it is safer than maximum distortion energy theory, which we have discussed in the first most class of the design of mission elements. So we have compared both theories and we have finalized which theory is safe. So for more conservative, which we have to take theory, which theory we have to consider, and for application purpose, which theory we have to consider. So now based on the maximum shear stress theory, it is given by the mission element will fail when the maximum shear stress will be equal to the yield strength of the specimen, so which we have seen in the theories of failures. Now that equation is given as tau max equal to SYT divided by 2 into FOS. So here the yield strength is given. So if directly shear stress is given, then we can say tau max equal to SYS divided by FOS. Now we have seen this previous classes also. So let us see what are the stresses in the mission element. So this element, let us consider the particular element in the shaft and what type of forces. We have seen two types of forces, that is due to twisting moment, that is the shear stress, and due to the bending moment, bending stress is generated. So let us calculate what are those stresses. So the bending moment of the circular shaft is given in the strength of materials, that is 32 m by pi d cube, and the shear stress is also given in the strength of materials, that is tau equal to 16t by pi d cube. Now in order to calculate the tau maximum, we need principal stresses. So by calculating the principal stresses only, we can apply the values of tau 1 and sigma 1 and sigma 2 in this equation by considering both these stresses. So the principal stresses based on maximum shear stress theory is given by sigma 1 2 equal to sigma x plus sigma y divided by 2 plus or minus root of sigma x minus sigma y divided by 2 whole square plus tau xy square. So this equation sigma x plus sigma y, here there are two types of stresses. So in this we don't have third direction. So that third direction is eliminated. The only stress which can be generated is the bending stress. So we can write it as sigma b divided by 2 plus or minus root of sigma by b divided by 2 whole square plus tau square. Now substituting the values of the stresses sigma b and tau in this equation, we get 16m by pi d cube plus or minus root of 16m by pi d cube whole square plus 16t by pi d cube whole square. So these all are derived in the strength of materials. So now in this equation, let us take 16 by pi d cube as common and let us write the equation. So the equation we will get for the principal stresses, that is sigma 1 2 equal to 16 by pi d cube into m plus or minus root of m square plus t square. Now if we solve the equation with respect to plus symbol, then we get sigma 1, and if we solve with respect to minus symbol, we get sigma 2. So there are two principal stresses generated in the element. Now if we substitute these principal stresses in the equation tau max, then we get the value of the diameter of the safe diameter of the shaft, that is given by tau max equal to sigma 1 minus sigma 2 divided by 2. So which will be given as, by solving the values sigma 1 and sigma 2, then we get 16 by pi d cube root of m square plus t square. Now this is entirely about based on strength. Now on the based of rigidity, we calculate as by using the torque equation, that is T by J equal to G theta by L. So that is given by theta equal to T into L divided by G into J. So here J we know the value, that is pi by 32 d power 4. So that is given by T into L divided by G pi divided by 32 d power 4. So from this equation we take d power 4 equal to 32 T into L divided by G pi theta. So this is the safe value for the diameter based on rigidity. From this equation we can calculate the diameter based on the strength. So we have two diameters, one is based on the strength and other one is based on the rigidity. Now which theory we have to, so on the which basis we have to find the value which is safer. So if we take based on the strength, we get the value of diameter as 80 mm, and based on the rigidity we get the value of diameter as 100 mm. Now which basis we have to finalize the safe diameter, that is for the diameter purpose we have to take the maximum value. So for any dimensional values, so while comparing two equations we have to take the maximum value as the safer value. Here we have to take the maximum value for the diameter calculations. When the amount of load is applied, then we have to take the minimum values. The stresses which are generated, we have to take the minimum values. For any dimensional values, that is the diameter, length, width, breadth or anything, we have to take the maximum value which will give the safe value for the design. So this is entirely about design of shafts based on the strength and based on the rigidity. Now let us solve a problem based on the strength and let us find the safe diameter of the shaft. A solid circular shaft is subjected to a bending moment of 3000 Newton meter. So they have given the value of M, that is 3000 Newton meter, and a torque of 10,000 Newton meter. So they have given the value of T. Now the shaft is made of 45C8 steel having ultimate shear stress of 500 megapascal. So they have given the value of max ultimate shear stress. So that is SYS So we have to write the equation as tau max equal to SYS divided by FOS. We should not take SYT divided by 2 into FOS. Now assume FOS is 6, determine the dia of the shaft. So they have given the value of factor of safety also. So now we have to consider on the basis of maximum shear stress theory, we have to solve the problem. That is tau max equal to SYS divided by FOS. So the tau max is given by 16 by pi d cube root of m square plus t square equal to SYS divided by FOS. So if we substitute the values of m, t, SYS and FOS, then the equation is written as 16 by pi d cube equal to root of 3000 square plus 10,000 square into 10 cube. Why? Because the values are in Newton meter. We have to convert into mm, or either we have to convert this into in terms of meter square. So this is nothing but Newton per mm square. So either we have to convert this or we have to convert this. So I have taken conversion for bending moment and torque. So that is 10 cube equal to 500 divided by 6. So by simply solving this equation, then we get the value of the safe diameter of the shaft, that is 86 mm. So by designing this in these conditions, if the diameter of the shaft is 86 mm, the design is safe. So it should be more than the value of 86 mm. If it is less than 86 mm, then the shaft may be go for a yielding or it may be get fractured. So the safe diameter calculated is 86 mm. So this is entirely about design of shafts. This is very easy topic. This also will be seen in strength of materials very clearly. So this only on the basis of maximum shear stress theory we have solved a numerical. So this is entirely about design of shafts. Thank you for watching this video. Subscribe to WB Institution for more videos.